Hello, this is part two of a video on showing some equations for energy. And I have to make two videos because Screencastify only lets me make them 5 minutes at a time. So we were talking about gravitational potential energy, and we said that gravitational potential energy depends on the mass of the object, the acceleration due to gravity on that planet, wherever you are, and then the height of the object. And we illustrated that showing a rock on a hill. And if we think about that, this rock has no height at all. So if we put that height in this equation, we would get zero potential energy. And that is what you should have been drawing in your pie charts, that whenever a rock is at the bottom of the hill or on the floor or something like that, it has zero gravitational potential energy. But when it's at the top of a hill, of course, it's storing some energy. It may at some point roll down the hill, and that energy will convert to kinetic energy. Okay. Now, looking at the units again, the mass would be given in kilograms. The acceleration due to gravity is meters per second every second, and the height is given in meters also. So if you think about those units now, we have kilograms, meters per second every second, so that seconds is in there twice, and the height is given in meters. So this whole thing is kilograms, meters squared, because there's 2 meters in there, and then seconds squared in the denominator. Kilogram meters squared per second squared is our energy unit, but that is actually a Newton because mass times gravity, we already know that mass times gravity is a Newton. That's how we found our force, and then times one more meter. Okay, so newtons times meters is a joule. Now, what about kinetic energy? If this rock rolls down the hill, it's going to gradually get faster as it rolls down the hill because it's accelerating due to gravity. Well, as it's getting down to the bottom of the hill, it has no more potential energy, no more gravitational potential energy. It can't go any farther down. It's just going to sit there eventually. All right. But as it goes down the hill, it does get faster. So it's converting that gravitational potential energy and it's storing it as kinetic energy down here. All right. So all this gravitational potential energy becomes kinetic energy by the time it gets to the bottom of the hill, assuming that there's no friction and we're not heating up the hillside with the rock rolling. Okay. So how do we get the kinetic energy? Kinetic energy is given by this equation, which is 1/2 mass times velocity squared. Now, why is it 1/2 mass times velocity squared? Well, I'm not going to show you the derivation of that equation actually, but we can take a look at that and remember if we took these units here, we saw that they had kilograms and then it had meters squared because it was meters in the acceleration times meters in the height, so that's meters squared, and then we had seconds squared here, seconds times seconds. All right, well, this is going to be the same because velocity is meters per second and it's squared, so it's meters squared per second squared times the mass, which is in kilograms. All right, so it's kilograms meters squared per second squared for our units. Okay, and so those units again are a Newton times a meter and in joules. Okay, so one thing about this is you have to realize that this is the variable that is the mass. All right, that does not mean meters there. It means the mass. Sometimes you guys confuse units with variables, and in the equation, it's the variable that's given here, and the units on our velocity is meters. Even though they look the same, one is the variable and one is the units. All right, so you have 3 equations. You're going to be doing some problems today with these equations, and there'll be simple problems, so you're just answering some questions about how well you maybe convert these one to another.